Hello everyone. In a previous video, I put some relatively tiny motors on my custom 6-inch drone, the Tubular Quad. If you're interested in seeing that flight footage and how that went, make sure to check out that video. But in summary, the smaller motors had less full throttle thrust than the larger motors. No surprise there. But I wasn't really able to tell a significant difference in the responsiveness of the smaller motors versus the larger motors. So that really had me thinking, because a lot of times I've heard that bigger motors have better response. So I wanted to test this or investigate this a little bit more. So what I could do is just buy a bunch of different sized motors, slap them on the quad, and then kind of fly the quad around and say, oh, this one feels more responsive. But that's kind of subjective-ish and not very precise. So instead, what I've done is I've come up with a mathematical function to express the relationship between motor size and response time. So that's what we're going to take a look at in this video. All right, buckle up. I've got the lecture slides and the laser pointer out, so you know you're about to learn something. So the claim that we're addressing is that bigger motors improve quadcopter response because they have more torque. So this at first makes sense because bigger motors have more torque, so they can spin the prop up and down faster, which should give the quad better response. But there are some factors that are not considered in that statement. So when you go up in motor size, the motor gets heavier, and you're adding that weight to the ends of the arms, and it increases the quadcopter's overall moment of inertia. And when you increase moment of inertia, it actually makes the quadcopter harder to change its rate of rotation. Also, when you go to a bigger motor size, the bell itself gets bigger and heavier, which increases its moment of inertia. So the bigger stator size has to somewhat fight against that bigger bell. So I wanted to try to take all of these things into account and see if bigger motors are better. So before we get into the nitty-gritty, I just want to say I'm just some guy on the internet. I'm not some genius or a mathematician. And also, I'm the only one who's checked my work. I think I haven't made any mistakes, but I still could have made mistakes. So let me know down in the comments if there are some blatant errors that I've made. And also, this study is basically purely mathematical and there's no data to back up the results. So take all this with a grain of salt. So what are we looking for? We want to know the relationship between the size of the motor and how responsive the quad is. So to express the size of the motor, we could just say it's stator volume or motor torque. And to quantify how responsive the quad is, response time, in my opinion, is the best metric. So basically, how long does it take the quad to go from just cruising along to spinning very fast? And the shorter that amount of time, the better. So we're trying to choose the motor size that minimizes the response time. The first assumption we're going to make is that the motors are saturated. What that means is the flight controller and ESC are just telling the motors to accelerate as fast as they can to get that quad rotating. And the reason this is important is because if you don't have your PIDs tuned correctly for fast maneuvers, your flight controller is not actually going to ask for maximum torque from the motors. So this assumption gets the PIDs kind of out of the equation completely and just says that the motors are trying to accelerate the quad as fast as possible. So next assumption is that motor torque is assumed proportional to stator volume. So anytime you see the subscript M, that's referring to the motor. Anytime you see the subscript Q, that's referring to the entire quadcopter. Tau is torque, so torque of the motor is proportional to stator volume Vm. So a lot of the math for this derivation is just trying to get everything in terms of time and motor torque, because those are the things we're going to plot at the end to see the effect of motor size and motor torque on response time. So this is the first time we're doing that. We want the motor mass to be expressed in terms of motor torque, because we know as we go to a bigger, torqueier motor that the motor mass increases. So how do we express that? Well, first we're going to assume that the motor mass increases linearly with stator volume. And since we know that stator volume is proportional to motor torque, we can say that motor mass also increases linearly with motor torque. So motor mass is mm. It's just going to be in slope-intercept form. In this case, y equals b plus mx. So Our intercept is MMO, which is a kind of abstract theoretical motor mass for a motor that has no stator volume. The slope is going to be the torque of the motor, tau m, times a constant, which just converts the units to play nice. So Cm is the motor mass constant, and it is the increase in motor mass per increase in motor torque. We're just getting motor mass in terms of motor torque on this slide. And we're going to do a similar thing for the moment of inertia of the motor. Now, this moment of inertia, IB, is just the moment of inertia of the rotating assembly of the motor. So it's mostly just the bell. So I've used the subscript B, but it's also like the shaft and the circlip at the bottom or whatever else. We're going to assume that this also increases linearly with stator volume or motor torque. And this assumption is most accurate when you're only changing the height of the stator. If you were only changing the diameter or radius of the stator, a cubic relationship would actually be more accurate, but we're just gonna keep it linear to keep things simpler. And this actually favors the solution of a larger motor as the ideal motor size, because we're not penalizing the larger motor size as much with a quadratically or cubically increasing moment of inertia of the bell. We have our intercept, IB naught, which is the theoretical moment of inertia of a motor bell with no stator volume. So once again, an abstract concept, plus the motor torque tau m times the rotating assembly constant. So how much the bell moment of inertia increases per increase in motor torque. Now let's figure out the angular acceleration of the motor, or how fast the motor can change its speed. So the general angular acceleration equation is alpha angular acceleration equals tau torque divided by I moment of inertia. So we know that the torque in our case is just the motor torque tau m, and the moment of inertia is what the motor has to change the speed of, and that is the prop, so IP, plus the bell of the motor, or the rotating assembly of the motor, IB. And we can just substitute in the expression we found for IB on the previous slide, and that gives us this equation at the bottom. So we can actually plot the motor angular acceleration versus the motor torque from that equation we just found. And it turns out that as you increase the motor size and motor torque, there's actually diminishing returns due to the fact that the motor bell moment of inertia is also increasing. So we'll see how this plays out later. Next up is the motor response curve, or basically the torque versus the RPM. So this graph on the left is from Mini Quad Test Bench, and this is a motor going from idle to 100% throttle as fast as it can. You can see it's a bit of this S shape, but that's pretty close to linear, so we're just gonna say it's linear for the sake of making the math easier. Another important assumption for this analysis is we're going to assume that the motor is constantly changing speed for the entirety of the response time. And the reason we assume this is because in reality, it doesn't take the quadcopter very long to go from 0 to, say, 1,000 degrees per second. So we're gonna assume that the motor doesn't run out of RPM before it reaches that desired rate of rotation. And our variable for angular velocity is omega, so angular velocity of the motor is omega m. Our next assumption is that the propeller thrust is proportional to the angular velocity of the motor, how fast the motor is spinning. I'm using Fm for force of the motor as the thrust that is generated at the motor. And then, of course, we have our angular velocity, omega m. So we're basically saying, you know, if you were to double the RPM of the motor, you're going to double the thrust of the propeller. And from the propeller thrust graphs I've seen, a linear assumption is actually a pretty good assumption. So we can actually combine those two previous graphs to figure out how fast the thrust increases as time goes on. So we actually assume that the vertical intercept is 0 because the initial motor thrust when the quad is just cruising doesn't matter because there's two motors pushing up on one side, two motors pushing up on the other side, so their torques on the quad cancel out. So we ignore the vertical intercept and we're left with the propeller thrust constant, which is the increase in thrust per increase in angular velocity of the motor, CP, times the angular acceleration of the motor, alpha m, times time t. And since we already have an expression for the motor angular acceleration alpha m, we can just throw that into our motor thrust equation and we get this expression. So now we have motor thrust in terms of torque of the motor and time. So that gets us closer to plotting response time versus motor torque. So we've done a bunch of math regarding the motors themselves. Now we need to do some math about the entire quad. So we want to figure out how the thrust from the motors impacts the way that the quad can change its entire rate of rotation. So the general equation for torque is that the torque tau is equal to the force F cross the distance between the axis of rotation and where the force F is applied, R. In our case, we're saying that there's torque imparted on the quad from all 4 motors, and we're going to assume that 2 motors are speeding up and 2 are slowing down. You could say 2 are at idle and 2 are speeding up, but that's really not going to matter because it's not going to change the shape of the graph when we're done. So we got 4 motors imparting a torque on the quad times the force from the motors, or the thrust of the motors, Fm, times the distance between the axis of rotation, which we're going to look at the roll axis, and the motor itself. So that distance is R on this figure, but we can actually get it in terms of the arm length of the quad, L, by just saying that R is equal to L times cosine of this angle theta. And now we can substitute in the expression we found for the thrust of the motor Fm into the torque imparted on the quad, tau q, and we get this expression at the bottom. Now we need an expression for the entire quadcopter's moment of inertia, IQ. So we're going to break this up again into IQ naught, which is the moment of inertia of everything on the quad except for the motors, plus the moment of inertia contribution from the motors, IM. We're going to assume that IQ naught is constant just for simplicity, and this is basically assuming that the weight of the quad doesn't change, which also is assuming that the battery size isn't changing. And this is an important assumption because generally you would want to run a larger battery with a larger motor size. And the reason for this is because larger motors can produce more torque and require more power. So you generally want to run a larger battery that can provide more power to those bigger motors. However, to keep the math simple, we're going to say, this battery is just a constant size and it can provide infinite power for an infinitely large motor. But this assumption is basically favoring the solution of larger motors because in the real world, you would increase the battery size, which would increase the quad's moment of inertia and would penalize going to the larger motor with a bigger battery. Now to get our expression for IM, we're just going to treat the motors as a point mass to keep things, once again, nice and simple. So moment of inertia from a point mass is mass m times r squared, radius squared. So we have 4 motors, so we have 4 out in front times mass of the motor is mm times radius squared. Once again, radius is L cosine theta squared. And then we can substitute in the expression we've already found for motor mass mm. It is at the end of the expression here. And then we can substitute Im into our initial expression for the entire quadcopter's moment of inertia. So we are expressing the fact that the moment of inertia of the quad increases as we increase the size or torque of the motor. So now we can come up with an expression for the quadcopter's angular acceleration, or just how fast it can change its rate of rotation. So using the same angular acceleration equation, alpha angular acceleration equals torque tau divided by moment of inertia I. We have expressions for tau q and IQ, so we just plug those in and voila, we have our expression for quadcopter angular acceleration. So now our angular acceleration is in terms of motor torque and time, which is just what we wanted because we want to plot those two against each other. So all we have to do now is a little bit of calculus. So the definition of angular acceleration is that it is the derivative of angular velocity. So alpha q equals d omega q dt, and we can rearrange and integrate, and we sub in for alpha q, so we get this scary looking expression, but it's really not that scary because we're integrating with respect to time. So it's just going to be time that we care about. So it's just going to be t squared over 2. And then on the right It's technically omega q final minus omega q initial, which I'm just calling delta omega q, which is our change in angular velocity. So if we're saying, for example, that the quadcopter is going from 0 to 1,000 degrees per second, we would just plug in 1,000 degrees per second for delta omega q. Now we just have to do some algebra to solve for time and then simplify the denominator, and that is our resulting function. So now we can plot the function with our motor torque or motor size on the horizontal axis and our response time on the vertical axis. And feel free to pause on this slide to examine our final equation and look at the definitions of all the variables. So I don't have actual numbers to plug into all of the constants in the equation, but the general shape of the graph is going to stay the same no matter what numbers you plug in. So we can make some general analysis based on the shape of this graph. If we start with a motor of basically 0 stator size, the response time is infinity. And that makes sense. If the quadcopter has an infinitely tiny motor, it's not going to be able to change its rate of rotation. Now, on the other hand, as the motor size or motor torque goes to infinity and gets really, really big, so you have a motor bigger than the universe, the response time actually also goes to infinity. As you can see where this blue arrow is pointing, this is actually the ideal motor torque or motor size, because that is where the response time is lowest. Because remember, we want the lowest possible response time. That is going to be the quickest responding and snappiest feeling quad. So if this graph went to 0 as torque went to infinity, then we would say bigger motors are always better. But as the motor torque and size goes to infinity, the response time keeps on increasing. So that actually means bigger motors are not better, and there is a singular minimum point, so there is a singular ideal motor size. Now you may be asking, well, what is that singular ideal motor size? And it actually depends, because each quad is going to have different properties, and the different properties change the values of the variables in this equation, which changes the value of the ideal motor torque or ideal motor size. So the one variable I explicitly want to show you guys is IQ0, which is our quadcopter moment of inertia excluding the motors. So we can generally say that a smaller, lighter quad is going to have a lower IQ0 than a bigger, heavier quad. So with that in mind, we can take a look at our handy dandy online graphing calculator, and we see that this gray point here is the minimum point. And you can say I plugged in all ones here because I don't have real values. If we start out with our smaller, lighter quad with an IQ0 of 1, and we increase the value to a bigger, heavier quad, you can see that that minimum point is moving upwards and to the right. So what does that mean? That means that because it's moving upwards, the minimum possible response time is higher than for a smaller, lighter quad. So even if you put a big torquey motor on a big heavy quad, you're not going to be able to match the minimum possible response time of a smaller, lighter quad. So that means if you care about maximum responsiveness, maximum snappiness, you need to prioritize lowering the weight and moment of inertia of your quad, because that is going to lower your minimum possible response time. And we also saw that the minimum point goes to the right as we go to the bigger, heavier quad. And that means that you need a bigger, heavier, more torquey motor just to achieve the minimum possible response time for that bigger, heavier quad. So as you just saw, the really cool thing about this equation is that we can not only examine the relationship between response time and motor torque, but we can also look at how other variables like the quadcopter's moment of inertia impact the response time and the ideal motor size. Let me know in the comments if you want to see a future video of me fooling around with the other variables such as arm length L, because that could be pretty interesting. Does a larger arm length lead to better or worse response. So potential next steps would be plug in actual numbers into the equation so that the equation would spit out the ideal stator size or ideal motor torque. Now, I don't really see a lot of practical use for this, given that we made a lot of assumptions, so the result probably isn't going to be very accurate, and the fact that everyone's quad is slightly different and each individual quad is going to have its own unique individual ideal motor size. Something probably more interesting and more useful would be to collect actual response time data with different stator sizes. So buy a bunch of motors and then see if there really is that minimum point. If we keep increasing the motor size too much or decreasing it too much, and we could also do a similar mathematical analysis to examine the yaw response, because the physics of the yaw axis are not quite the same as the pitch and the roll axis. So that is about it for this video. In summary, bigger motors are not always better. There is actually a singular ideal motor size based on the properties of your quad. And if you want to minimize the response time of your quad as much as possible, you should try to lower the weight and moment of inertia of your quad as much as possible. So if you enjoyed this video or learned something from it, make sure to give the video a like. Let me know in the comments what you thought, if I made any errors, and if you want to see more nerdy videos like this in the future, like examining the impact of arm length on response time. If you got value out of this video or you're using an ad blocker, please consider supporting me on Patreon. Link to the Patreon, Discord, and Instagram are in the description below. Thanks for watching.